This is Chapter 1, Problem number 3, from the book Randall D. Knight, Physics for Scientists and Engineers. The problem states that you're driving along a highway going at 60 miles per hour. This clearly means that you are going at constant speed. If the speed is constant, I can draw my motion diagram, dots that are equally spaced apart. I will also indicate that this happens at time equals 0. Notice that you notice a speed limit sign that says that it's 30 miles per hour, and the idea is that you slow down quickly but not instantly. So as you slow down, it happens rather quickly, and when you slow down, you continue going at speed 30 miles per hour. As an icing on the cupcake, we can draw our velocity vectors to complete our diagram. Initially, this is an area of constant speed. This is an area when you start slowing down your vehicle. And this is the area when you are going at constant speed again of 30 miles per hour. I would also like to indicate that when you notice the speed limit sign, as the problem states, that happens at 30 seconds. And until the end of this clip, that also happens at 60 seconds. I would also like to add acceleration vectors to clearly indicate that you are slowing down, and once you completely slow down, you are going at constant speed. So these velocity vectors are equally spaced. And that's problem number 3. Problem number 7. A softball player slides into the second base, and we once again have to use the particle model to draw a motion diagram showing his position and his average velocity vectors from times he begins to slide until he reaches the base. Clearly, throughout the whole frame, the player is slowing down. I will first indicate a rather large spacing between the dots, and then the spacing gets smaller and smaller as the player completely slows down to a complete stop. As we do with motion diagrams, we connect them with vectors. There they are. I would also like to indicate that this is where the player stops. I guess I can write start here to indicate this is the beginning of the frame. I will also label my velocity vectors. There they are. And let us also include acceleration vectors, because throughout this whole frame you are slowing down until you slow down to a complete stop once you reach the second base. Alright. Problem number 10. So example 110 shows 2 dots of a motion diagram and vector v1. There it is. Sorry about the bad picture. Copy this figure and add vector v2 and dot 3 if the acceleration vector is either pointing up or pointing down. We will actually do both cases. So let's reproduce that same image. There it is. This is vector 1. Dot 1, dot 2, we're naming dots, I guess. And if the acceleration vector is pointing up, what will we see? Well, because the acceleration vector is the same direction as velocity vector, the velocity vector should get longer. So that means you will go faster. Let's add, this is going to be dot number 3. And this is going to be velocity vector 2. There it is. Now let's reproduce that same image again. 1, 2. This time, what if the acceleration vector is pointing down? So it's pointing this way. What will happen to velocity? the velocity should get smaller, so you will go slower. That means you're slowing down because acceleration vector points in the opposite direction of velocity. And that's why I draw a shorter velocity vector that it is. And that is essentially it for this problem. Problem number 17. A toy car rolls down a ramp, then across a smooth horizontal floor. Draw a complete motion diagram of the toy car. Right, so initially a toy car starts on the ramp and it's rolling down. An object that is rolling down is feeling acceleration. Let's just add one more dot. Alright, that is denoted by these dots being further apart. And then it comes across a smooth horizontal floor. That means it doesn't feel any other forces, so that means it's going at constant speed. And I can denote it by having velocity vectors that are equal in size. So all that's left, you probably know the drill, is just draw these arrows. There they are. Oops. These are meant to be equal in size. I will also label them. The arrow over the velocity vector is very important. And we will add one more piece of information. Because it is rolling down a hill, it is feeling acceleration that is in the same direction as its velocity. Hence the acceleration. And that's why velocity is changing in size. And that is problem number 17. Problem number 18. This problem is a very interesting problem because it has multiple parts and it's kind of long. And that is why I included a book this time. It shows a motion diagram of a drag racer, and the camera took one frame every 2 seconds. That tells us that each dot will represent a separation of 2 seconds. Also, we have this indicator of the x-axis, or the position of the drag racer, and it is obviously in meters. So let us begin by drawing a table. I happen to have a straight edge with me. Very convenient tool. A asks us to draw a table of time versus position. I will also include the number of dots. It will make this problem a little bit easier. There happens to be 9 dots. Alright, at this column I will have time in seconds, and this will be the position, or x, and that is going to be in meters. So the time of the first dot, if you look at this image closely, we will hopefully all agree on that happened at time 0. Each dot represents a separation of 2 seconds. So all we have to do is just increment the time of each dot by 2 seconds. Just like so. Now this might be a little bit of a tricky part, but all we have to do is looking at each dot, find the position. So looking at the x-axis. The position of dot 0 occurred at 0 meters, that's what it looks like to me. The position of the second dot, well, it's kind of hard to tell, but I'm going to give it 30 meters. The position of the second dot, it looks like 95 meters, 210 meters, 400 meters, 510 meters, 600 meters, 675 meters, and finally 720 meters. I was able to tell these values just by looking at this table. That's all I did. There's nothing special about this. And that answers the question A. B. Now we have to make a position versus time graph for this drag racer. Thankfully, we have a table above, so let us draw the axes. Hopefully you can do it with a straight edge. If not, it's okay. It doesn't have to be perfect. On this axis, our dependent axis, I will probably put the time, and the time is going to be in seconds. Right? So that is my dependent axis, the x-axis. And on the y-axis, I will put the position. Our next step is just to graph these values. And that is all we have to do. And this is hopefully what you get after you graph all of these values. And that's it for problem number 18. Problem number 22. Draw a pictorial representation of the following problem and do not solve the problem because this is only chapter 1. What acceleration does a rocket need to reach a speed of 200 meters per second at a height of 1 kilometer? So we are asked to draw a pictorial representation. I'll just use our dot diagram that we have been using for the past few problems. So a rocket starts from rest and it needs to reach the speed of 200 meters per second. The way we can represent that is by spacing the dots further and further apart until it reaches 200 meters per second. The fact that it starts from rest is assumed in this problem, as you will learn to assume a lot of things in physics. Alright, I will draw my arrows. And this is not a formal dot diagram that we have been drawing for the past few problems. This one is going to be a little bit different. What I like to do is I like to list all the knowns and the unknowns. This will help us a lot in the problem solving step of this problem. So from this problem, because we start from rest, our initial velocity, v of I means velocity initial, and because we're going up, we're going to say it's flying in the y direction. You will have to learn how to do that also on your own problems. And it's going at 0 meters per second initially. We also know the final speed as well. Our final speed needs to be 200 meters per second. Alright? So what else do we know? Well, we also know the final height. I will call it delta y. The displacement in the y direction is 1,000 meters. It lists 1 kilometer, but what I like to do to list for all my knowns is to keep it in SI units. And we will do plenty of practice with that. So delta y is 1,000 meters. The unknowns. Well, we are asked for the acceleration. Alright, and the acceleration is in the y direction, and we simply don't know it yet. We don't need to solve the problem, and this is how we would set it up. Problem number 25. Just as promised, we will do a little bit of SI unit conversion. 3 hours is not in SI units. As you probably know, the SI units for time is seconds. So our goal is to convert hours into seconds. Let's do it. So first we know that there are 60 minutes in 1 hour. Let me multiply it by hours. The reason why I'm putting hours on the bottom is that way when I multiply, the hours units will cancel. You always want to do that in conversion problems. 60 minutes. Alright, so we will get minutes out of this. That's not what we want yet. We want seconds. Let's put minutes on the bottom again. 1 minute is exactly 60 seconds. Oh, fine, I'll write that in. Alright, and now we're ready to do our final conversion. As you can see, the minutes and the hours cancel, and we should get accurate to 3 significant figures the following answer: seconds. Thankfully, this is in SI units. B. We have to convert 2 days into seconds again, because the SI units for time is once again seconds. Alright, so let's take it one step at a time. In one day, there are exactly 24 hours. Alright, that way the days will cancel when we multiply. But notice, we just created our own convergence factor. In 1 hour, there are exactly 60 times 60 seconds. So there are exactly 3,600 seconds in 1 hour. That's amazing. Alright, these will cancel again. And we should arrive at our answer. Seconds. I boxed my answer. 3 significant figures. We will do a little bit of practice with significant figures as well, so don't worry. C. We have to convert one year into, once again, seconds. Alright. How many days are in a year? Alright, let's put year on the bottom of it again, because we want to cancel the year. There are exactly, well, not exactly, I will say there's 365 days in 1 year. And then we multiply by, we could do all these steps again, but once again notice that we just created our own conversion factor between days and seconds. And the conversion factor is 365 days has exactly 90,000 seconds. Alright? That way the days will cancel, the years will cancel, and our magical answer accurate to 3 significant figures will be 10 to the 7 seconds. D. Now this one might be a little bit more tricky than the ones we have been dealing with. We have to convert to SI units. The SI units for speed is meters per second. So the second dimension is correct, but feet are not correct. So let's convert. 1 foot has 12 inches. Right? That will cancel the feet, but we're left with inches. That's not good. So 1 inch has 2.54 centimeters. Alright, after the inches will cancel, we're left with centimeters. But centimeters are not SI units. They are metric, but they're not SI units. We have to convert it to meters. Alright, now since we're converting to meters, we know meters are going to be on top, centimeters are going to be on the bottom, and there are exactly 100 centimeters in 1 meter. There we go. And if we multiply all of this together with centimeters canceling, we should get 65.5 meters per second. And that is the answer to D. Problem number 29. Just as I practice, we'll be practicing a little bit of significant figures and the rules with significant figures, especially the ones that are adopted in this book. So first problem asks to give us an answer in 3 significant figures. This number we can just plug into our calculator. Remember that exponentiation is the same thing as multiplying this number 3 times. And each time we have to keep in mind that we keep 3 significant figures. The answer that we would get after multiplying all of this together is the following. But as you can see, this is well beyond 3 significant figures. So we have 2 options. We can either leave our answer like this, assuming that these are the significant digits, so 3 significant figures. My favorite one is this one, 1.95, 3 significant figures exactly, times 10 to the 3rd power. I love this one a little bit more, the scientific notation. Next problem. This one is a little bit more simpler. So multiplying these numbers together, we get 65.1 125. I did it in my calculator. There's no way I can do this in my head. Alright, and we have to preserve three significant figures. Well, we have 61.1. In this case, it's appropriate to leave our answer like this, because there is no hanging zeros. Or we can also turn it into a scientific notation, which looks a little bit weird. But this time I would prefer this one. Next question. This one is a little bit tricky, so first we have to find what is the square root of 12.5. Let me plug it into my calculator. Square root of 12.5 is 3.535, and I'm leaving all the other digits alone. And then we're subtracting 1.2. So the rules with multiplication is that you always choose the smallest number of significant figures. The rules with subtraction and addition is that you just carry out your subtraction or addition, and some people, what they do is they draw this line and they just do their addition. 5 plus 2 is 7, and 3, I'm sorry, I did addition. 5 minus 2 is 3, sorry about that. 3 minus 1 is 2, alright? And then we just essentially just forget about those bits, and our answer to the correct amounts of significant figures is 2.3. Next question. This question seems tricky, but it's actually not tricky. 1 divided by 12.5. That's the same as division, and our answer should be 0.08, and then we add another 0 because this is three significant figures. We are treating that 1 as if it has what's called infinite number of significant figures. It's an implied number. And this number I would love to convert to scientific notation. It just looks better like that. Here we go. And that is all the rules with significant figures. Just remember, when you multiply, you choose the smallest number of significant figures. And when you add or subtract, just apply the following rule. The number that is the shortest, you're going to draw a bar across it. And that's it. Problem number 43. Alright, I decided to choose one hard one. David is driving a steady 30 meters per second when he passes Tina, who is sitting in her car at rest. Tina begins to accelerate at a steady 2 meters per second squared at the instant when David passes her. How far does Tina drive before passing David? And we are told to not solve the problem, but just set it up. I think a good way to start is by drawing our dot diagrams that we have been drawing before. Alright? So David, it says that he's going a steady speed of 30 meters per second. That means we draw dots that are equally spaced apart. There they are. Okay? And then we connect them with arrows. So that is David. Now David has been driving for 30 meters per second probably before he met Tina, but we don't worry about that. It's not important. The important part at t equals 0 is when Tina begins to accelerate to catch up to David. So this is the only time when we start carrying. So I'm going to draw Tina, and she starts from rest and is steady accelerating. Okay. And we are asked how far does Tina drive before she passes David. I guess a good thing to indicate is that Tina is accelerating all this time. That's Tina. Alright. So just like what I like to do is I always like to list all of my knowns and all the unknown. It's especially important in this problem because there are a lot of things that are going on here. So first, we know that David's velocity, David's initial velocity, and actually his final velocity as well. So v David I, that's velocity of David initially in the x direction. That's a lot of subscripts, but you're going to have to get used to that. And it is equal to velocity of David final and also in the x direction, and that's all 30 meters per second. Alright, so we know that. We also know that acceleration of David in the x direction is 0 meters per second squared. The reason why I'm not putting arrows over either one of these quantities is because I'm dealing with their magnitudes and not velocity or acceleration as a vector. Another piece of information that we know is that velocity of Tina initially and also in the x direction is actually 0 meters per second, and this is a very important 0. She is at rest. And velocity, well, we don't know the final velocity of Tina, but what we do know is that we know the acceleration of Tina in the x direction, and that's 2.0 meters per second squared, accurate to 2 significant figures. I guess we also know the initial time, which is 0 seconds, but it is not as important. These quantities are more important. They will allow us to solve this problem. The unknowns. What are we actually trying to find here? We are trying to find how far Tina drives before she catches up to David. And I will call that displacement in position in the x direction, delta x. And delta x is what we're trying to find in this problem. And that wraps it up, because we do not have to solve this problem. That's it. The last set of problems that I want to do out of this chapter, out of chapter 1, are these three. And that's just visually understanding what a dot diagram is trying to represent. So let's look at number 46. I'll try to limit my writing and do a little bit more talking. So looking at this diagram, the velocity vectors, they seem to be increasing in size, and after they reach this point, there is no acceleration, and velocity vectors are all the same size. Why would this happen? So looking at this, it looks like as if something is rolling down a hill. If I were to draw a cart, this dot diagram would perfectly represent this situation, because if this cart starts from rest and starts rolling down a hill, it will go faster and faster and faster and faster until it reaches this point where it continues on at a steady speed. So here it's accelerating, and here it is not accelerating, just like that diagram represents. 47. Alright, so it also looks like there's some object that starts from rest, and as it's moving downwards, it's gaining speed actually, and the acceleration is downwards too. But then this is the same point, so it resumes here, and it starts going up, but this time the acceleration is still downward, and it's still the same magnitude, and it's losing speed. What could this mean? Well, imagine if you're throwing a bouncy ball or a baseball downward, what would we see? So what we would see if we drop it from rest is we will see that it's accelerating downwards. Yes, it's accelerating downwards until it hits the ground. And then what happens when it hits the ground? It feels massive acceleration upwards because it changes direction. Velocity changes direction. Because velocity changes direction, let's start here, the ball will start going upwards. And it won't get as high as where it started off of. It loses some energy. But we also notice that acceleration is still downwards. That's weird. But that's what gravity does. Gravity pulls everything towards it. So this dot diagram perfectly describes that situation. Number 48. Sorry, it's going to get a little bit crowded here. Some object starts with some velocity initially, and the velocity is decreasing until it reaches this apex point, and then velocity starts increasing again. So decreasing, increasing. What could that mean? Well, imagine if I had a cart, and if I wanted to push it with some initial velocity. Alright, so it's going to have some initial velocity, but due to gravity, it will start losing speed, losing velocity, until it reaches this point. Then what would happen is it would start accelerating once again, once it starts rolling down the hill. So this dot diagram perfectly describes the situation. If I push the cart up the hill, it would be accelerated backwards, so it would lose speed until it reaches this point, and then it would start gaining speed again after passing that point when it's rolling down the hill. And that's it.